Okay, so now we'll talk about power. And it's defined as the rate at which energy is expended or absorbed. Energy is never, it's transformed. It's never destroyed. It just gets converted from one form to another. We use P to represent power, and we measure it in watts, named after James Watt, the steam engine guy. He invented a lot of stuff, and it mostly dealt with power things. So it was defined that a watt was equal to 1 joule per second, which is a measure of energy done per second. And a joule is defined as the opposite is 1 watt second. So if you have a joule for a second, if you have a watt for a second, that is equivalent to 1 joule of energy. And a joule is also equivalent to 1 coulomb volt. So we have a coulomb of charge at 1 volt, which is 1 joule of energy. So that's how energy gets back in with the charge thing. The potential and the amount of charge is energy. So we know that 1 watt is 1 coulomb per second times a volt, which means it's 1 ampere times a volt. And that's where you get the formula that power in watts is equal to current or coulombs per second times voltage. So we have a nice little pie chart, and this one actually spells pi. Same deal, okay? Put your finger over the parameter you're trying to solve for. So power is equal to current times voltage, or current is equal to power divided by voltage, or voltage is equal to power divided by current. So there's all those. Now, in some cases, you'll have resistance as a 4th element in there. So that's why I showed how you derive these other 2 formulas, where power is equal to the square of the voltage divided by the resistance, or the square of the current times the resistance. So in this little simple circuit, we have a 13.8 volt battery. And that's your typical 12 volt battery charge, nominal. And that's what amateur radio transceivers typically run on a 13.8 volt supply. They don't have a built-in power supply in most cases. It runs off of either a battery or a 13.8 volt power supply. So that's why I use this number. And if we had a 1.38 ohm resistor or load here, we're going to have 10 amps of current through it, right? Yeah. Okay. So 13.8 divided by 1.38 is 10. So how much power do we have dissipated in that resistance or that load? What was the formula? P equals
voltage times current.
right.
All right, you got 13.8 volts. You got 1.38 ohms. Right.
See, in this case, you know the current. Okay. So it's 10 amps at 13.8 volts, so it's gonna be 138 watts, right?
Yeah,
Okay. If we didn't know the current, or excuse me, if we didn't know the voltage, but I knew the resistance and I knew the current, then I could use this formula, okay, and square the current multiplied times the resistance and come up with 138 watts. If I didn't know the current, but I knew the voltage and the resistance, then I would square the voltage and divide it by the resistance and come up with 138 watts.
so all we have to do is times what we know to get what we don't know.
Yeah, pretty much. Now, the one thing that is important here to remember for future is the power formula, I squared R, is real power. The formula E times R, when we talk about alternating current, will be apparent power. Because you can have a phase shift between the current and the voltage. So you get a thing called power factor. So you can have, and the power company charges you on apparent power, not real power. So if I had a reactive load here, I could still have 138 watts of real power coming in, but because of that reactance, the apparent power may be 150, 200 watts, which is what they're going to charge me on, which is why you may have a thing called a power factor controller. They used to be popular a long time ago to reduce your power bill because it would correct the power factor. But that's the main place you'd want to use this I squared R formula is for real power as opposed to apparent power. In DC, they're the same. When you get to an AC circuit, if there's any kind of reactive component, they're going to be different. Just to confuse you some more. So, how much power is delivered by a voltage of 13.8 volts and a current of 20 amperes?
Hmm. 13.8, okay.
Now, I did this one because this is typical of a 100-watt amateur transmitter. Running at 13.8 volts, it's going to draw in the neighborhood of 20 amps if it's outputting 100 watts. But you're going to have 276 watts coming into it. So it's less than 50% efficient. You've got 276 to generate 100 on the end, hopefully at your antenna. So if I've got 12 volts and a current of 3 amps, how many watts?
3 times 12, 36.
All right.
Okay.
That might be like a headlight bulb on a car. How much current required to deliver 60 watts at a voltage of 12 volts? So now you know watts, you know voltage. You don't know current. So what's the current?
Hmm. 60 watts divided by 12 volts is 5 amps. So
Right. 5 amps. Okay, so what's on the test? What term describes the rate at which electrical energy is used?
peak current,
The rate at which electrical energy is used.
It's gonna be V or B, I voltage. Power could mean anything.
Power.
Yeah, power is it?
Power is the rate at which you're using energy.
Okay.
Electrical power is measured in which of the following units? Remember the steam engine guy?
Watts?
Watts. James Watt. What is the formula to calculate power in a DC circuit? One of those is correct.
Okay.
Alpha. How much power delivered by a voltage of 13.8 volts DC and a current of 10 amps? I think you've seen this one.
Um, 138 watts.
Yep. How much power delivered by 12 volts and a current of 2.5 amps?
Let's see. $14.5 watts. So we look at see.
2.5 amps.
It'd be,
If it was 2 amps, it would be what, 24 watts?
yeah, okay,
But it's 2.5. It's more, right?
so we're looking at 30 watts.
There you go. How much current is required to deliver 120 watts at a voltage of 12 volts?
So what I would want to multiply, 120 by 12. Be 132 amps. Wow.
Where you're trying to find current, so you'd be covering up the I. And then you would hydrogen.
So you got P divided by something, what?
How much from? See. Well,
P divided by E,
E's gonna be
12. P is 120.
112 amps. Let's see. No,
120 watts divided by 12 volts.
120 divided by 12. Will give you well, that'd be 12 amps.
No,
All right. Glass is on. All right. Be 10 amps.
there you go. Okay, so. We learned about the new pie chart that actually spells pi. You work it the same way. Put your finger over the parameter you're solving for. So the power is equal to the current times the voltage, or voltage times the current, doesn't matter what the order. Or it's the current squared times the resistance, or the voltage squared divided by the resistance. Those two things will come later on. And that a joule of energy is 1 coulomb times 1 volt. And a watt is 1 joule, how much 1 joule of energy per second that's being consumed. And therefore a watt is equal to 1 ampere times 1 volt. So that's how we get the power is equal to E, or I times E. Just remember to write your little pie chart. It'll help you remember it. That's what the back of the answer sheet is for.